What if I told you there's a concept in mathematics that connects it to physics, engineering, and even music? And that is this function. So how is it important in music? If you take the Fourier transform of a rectangle, if you add up all these sines and cosines, you get this rectangle. This is an ideal low-pass filter. But what if we wanted to find the area under this graph? And to do that, we take an integral. And the way we write this. So how do we do this? And this requires some calculus knowledge. Interestingly, the way that we solve this, it's called Leibniz rule for differentiating under the integral sign. If we use common ways for evaluating this integral, none of those will work. The function's symmetry lets us simplify. We're going to define a new function which has a parameter t, and so we're going to use what's called Leibniz technique for differentiating under the integral sign. We're going to differentiate this with respect to the parameter. This integral is possible to evaluate using normal integral techniques, and then we can factor. So notice that since t does not vary with x, we can take it out to the front, we can move this to the other side and factor. And now we just plug in our bounds. And we need to solve for this constant of integration by using a limit. We get this constant c is pi over 2. Now all we have to do is plug in 0 for t and we get our result. And our integral is solved with a value of pi. Our magic number, pi, connects mathematics, physics, engineering, and even music.